There are various types of machine learning (ML) models, each designed for different types of tasks. Below is a breakdown of the primary types of ML models and their common uses. Supervised learning models. Definition. In supervised learning, the model is trained on labeled data where the input-output pairs are known. Common uses. Regression, classification, prediction. Types of supervised learning models. Linear regression. Use. Predict continuous numerical values, e.g. predicting house prices. Logistic regression. Use binary classification problems, e.g. spam detection, disease diagnosis. Decision trees. Use classification and regression tasks, e.g. credit risk analysis, recommendation systems. Random forest. Use ensemble method for classification and regression, e.g. fraud detection, loan approval. Support vector machines, SVM. Use binary and multi-class classification, e.g. image recognition, text classification. K-nearest neighbors, KNN, use classification and regression, particularly for smaller datasets, e.g. recommendation systems, pattern recognition. Gradient boosting machines, GBM, use boosted decision trees used for regression and classification, e.g. financial modeling, risk prediction. Examples: XGBoost, LightGBM, CatBoost. Neural networks, ANN, use tasks involving high-dimensional data like image and speech recognition and classification. 2. Unsupervised learning models. Definition. In unsupervised learning, the model is trained on data without explicit labels. It identifies patterns or structures in the data. Common uses: clustering, anomaly detection, dimensionality reduction. Types of unsupervised learning models. K-means clustering. Use grouping similar data points into clusters, e.g. customer segmentation, document clustering. Hierarchical clustering. Use clustering with a tree-like structure for grouping data, e.g. gene sequence clustering, market research. Principal component analysis, PCUs, dimensionality reduction to simplify large datasets, e.g. reducing features in image processing or genetics. Autoencoders. Use neural networks for dimensionality reduction, image compression, and anomaly detection, e.g. data compression, denoising. Gaussian mixture models, GMM. Use probabilistic model for clustering based on mixture of Gaussian distributions, e.g. image segmentation, stock price analysis. 3. Semi-supervised learning models. Definition: combines a small amount of labeled data with a large amount of unlabeled data. Useful when labeling is expensive. Common uses: image classification, web content categorization. Example of semi-supervised models. Self-training models. Use initially trained on a small labeled dataset and gradually uses its predictions to label more data. Generative adversarial networks. Use can be used in semi-supervised learning to generate labeled data for improved model performance, e.g. improving image quality, synthesizing realistic images. 4. Reinforcement learning models. Definition: models learn by interacting with the environment and receiving feedback, rewards or penalties. Common uses: robotics, game AI, dynamic decision-making, recommendation systems. Types of reinforcement learning models. Q-learning. Use learn optimal actions to maximize reward in a given environment, e.g. autonomous driving, stock trading. Deep Q networks, DQN. Use combines Q-learning with deep learning for complex environments, e.g. game playing, like in Atari or AlphaGo. Policy gradient methods. Use directly optimizes the policy function, e.g. robotics, real-time decision-making. NASH 5. Deep learning models. Definition: subset of machine learning that uses neural networks with many layers, deep networks, to model complex patterns in data. Common uses: computer vision, natural language processing, NLP, speech recognition. Types of deep learning models. Convolutional. Use primarily used for image recognition and processing, e.g. facial recognition, object detection. Recurrent neural networks, RNNs. Use sequence prediction tasks, e.g. language modeling, time series forecasting. Long short-term memory networks. Use a type of RNN specialized for long-term dependencies, e.g. text generation, transformers. Use sequence-to-sequence tasks, e.g. natural language processing, translation, text summarization, used in models like GPT-BERT. 6. Ensemble learning models. Definition: combines multiple models to improve overall performance, accuracy, and robustness. Common uses: classification, regression, and improving predictive models. Types of ensemble models: bagging, bootstrap aggregating. Use: reduces variance by combining the output of multiple models, e.g. random forest. Boosting. Use: focuses on correcting the errors made by previous models, e.g. XGBoost, LightGBM. Stacking. Use: combines predictions from multiple different models, e.g. logistic regression on top of decision trees, SVMs, etc. 7 neural network variants. Feed-forward neural networks, FNN. Use: basic neural networks where connections do not form cycles, used for basic classification or regression tasks. Generative adversarial networks. Use: creates synthetic data that resembles real-world data, e.g. image generation, style transfer. Variational autoencoders, VAEs. Use: for generating new data points similar to the training set, e.g. image generation, drug discovery. 8 Bayesian models, Bayesian networks. Use: probabilistic models for decision-making and reasoning under uncertainty, e.g. risk assessment, medical diagnosis. Naive Bayes. Use: simple and fast classifier based on Bayes' theorem, often used in text classification, e.g. spam detection, sentiment analysis. Key takeaways. Supervised models are best for problems where labeled data is available, classification, regression. Unsupervised models are used for exploring hidden patterns in unlabeled data, clustering, dimensionality reduction. Reinforcement models are optimal for tasks requiring interaction with the environment and feedback, robotics, gaming. Deep learning models are specialized for complex tasks like image and speech recognition. Ensemble methods boost accuracy by combining multiple models. Each ML model type has strengths suited to different kinds of problems in various domains, such as finance, healthcare, retail, and technology. For large language models, LLMs, the models used are primarily based on deep learning architectures, specifically transformer models. From the list of machine learning models mentioned earlier, the most relevant ones for developing LLMs are: 1. Transformer models. Use: transformers are the backbone of almost all modern LLMs. These models process and generate language using an attention mechanism, allowing them to handle long-range dependencies in text. Examples: GPT, generative pre-trained transformer; BERT, bidirectional encoder representations from transformers; T5, and others. Common applications: text generation, summarization, translation, question answering systems, chatbots, code generation. Deep neural networks, DNN; feed-forward neural networks, FNN. In early stages, these networks might be used for simple language tasks, but are not as effective as transformers for complex text generation tasks. Use in LLMs. While feed-forward networks are the building blocks of many models, they are not typically used alone for LLMs due to their limitations in handling sequential data. However, the core structure of transformers is still based on deep neural network principles. 3. Recurrent neural networks, RNN, and LSTMs. Use. Historically, RNNs and LSTMs were used for sequence-based tasks such as language modeling and speech recognition. While they handle sequential data, their performance on long sequences is limited compared to transformers. Current status. RNNs and LSTMs have largely been replaced by transformers for LLMs due to their inability to handle long-range dependencies efficiently. Summary: LLMs are primarily built on transformer models because of their efficiency in processing and generating text through the attention mechanism. While other neural networks like RNNs and LSTMs were historically used for language tasks, transformers have surpassed them in performance for building state-of-the-art LLMs like GPT, BERT, and T5.